A two-person crew at a Gulf Coast liquid natural gas terminal walked past 180-degree steam lines just to note that a compressor bearing looked hot. That handwritten note went onto a clipboard, then into a spreadsheet, and stalled for 3 weeks. When the bearing finally seized, it destroyed the compressor and caused a 14-day shutdown. The gap between a human observing problem and the facility taking action cost $8 million. Sending standard wheeled or tracked robots to do this job is impossible. They cannot climb steep industrial stairs, navigate narrow graded catwalks, or function effectively in an environment dominated by 95 decibel ambient noise and extreme heat. To navigate unpredictable three-dimensional terrain, engineers realized the wheel had reached its absolute physical limit. The solution required looking at how biology traverses uneven ground. By decoding the evolutionary biomechanics of animals like dogs and horses, robotics teams are building machines capable of true all-terrain agility. Achieving autonomy in hazardous industrial zones requires a direct translation of biological movement into mechanical engineering. Classical mechanical gears, the exact kind used in traditional robotic arms, produce locomotion that is far too slow and rigid. Instead, a quadrupad relies on high-torque brushless DC motors and hydraulic actuators to serve as muscles. These components are required to absorb impulsive forces. This is the violent collision energy generated the moment a heavy metal foot strikes a solid floor. If a machine crawls slowly with 3 feet planted on the ground, it maintains static stability. But moving quickly requires dynamic stability, a process of deliberately falling forward and catching the body's weight with each successive step. To execute this fall, engineers applied the slip model, a spring-loaded inverted pendulum, mimicking an animal's elastic tendons. As the leg compresses on touchdown, it stores potential energy, releasing it on liftoff to recycle power and maintain high speed. Coupling impact-absorbing hardware with elastic motion enables a massive, rigid machine to navigate with the fluidity of a living organism. High-torque hardware and dynamic gates require a highly dense processing network. Vision cameras act as the visual cortex, scanning the environment to feed real-time, three-dimensional spatial data back to the main control board. The rhythm of the walk itself is controlled by central pattern generators. These bio-inspired algorithms act like a spinal cord, producing cyclic leg motions so the main brain doesn't have to calculate every individual step. When a foot slips on loose terrain, the robot relies on neuromorphic reinforcement learning. Instead of waiting for a main processor command, the system learns locally, executing a split-second micro-adjustment to the joint angles to catch its balance. This localized reflex-like learning loop prevents catastrophic falls, allowing the machine to adapt to chaotic environments exactly the way a biological creature does. These bio-inspired systems have transitioned from laboratory experiments into highly durable, production-grade tools. Using a direct sensor-to-motor connection, the robot actively moves toward a specific stimulus. It autonomously hunts down thermal anomalies, employing the same positive taxis behavior a search dog uses to track a scent. When a quadruped spots an overheating bearing, it doesn't leave a handwritten note. The robotic sensor data feeds directly into a computerized maintenance management system, instantly generating a prioritized digital work order. Facilities utilizing these systems report an 80% drop in humans entering dangerous confined spaces and a 70% reduction in the cost of routine inspections. By accurately mimicking millions of years of biological evolution, quadruped robots have successfully crossed the gap from theory to industrial deployment. In the world's most challenging environments, the future of robotic safety has 4 legs.